students. So welcome back. So this is my video lecture 7 on S block elements. So we were discussing about the chemical properties of S block elements, isn't it? We have discussed so many chemical properties. We are almost at the end now. So in the previous, I hope you have watched the previous videos. So in the previous videos, we have completed the reaction with oxygen, reaction with water, reaction with solubility in liquid ammonia, reaction with nitrogen, reaction with halogens, okay, and then formation of carbonates, correct? Okay, so now we will study the seventh chemical property of alkali metals and alkaline earth metals. What is it? Yes, it is formation of bicarbonates. Formation of bicarbonates. Formation of bicarbonates, or else that is also called as hydrogen carbonate. It is also called as hydrogen carbonate. Okay, so we have lithium, sodium, potassium, rubidium and cesium, isn't it? Lithium, sodium, potassium, rubidium and cesium in alkali metals. And in alkaline earth metals we have beryllium, magnesium, calcium, strontium and barium. See, all alkali metals will form bicarbonates of the type MHCO3. Okay, for example, lithium hydrogen carbonate or lithium bicarbonate, sodium hydrogen carbonate or sodium bicarbonate, okay, NaHCO3, LiHCO3, okay, potassium bicarbonate, KHCO3, rubidium bicarbonate, RbHCO3 and cesium bicarbonate, CSHCO3, cesium bicarbonate. Whereas all alkaline earth metals, okay, will form bicarbonates of the type M2, okay, HCO3, M2HCO3, okay. For example, sorry, M2HCO3 twice, MHCO3 twice. For example, okay, yes, beryllium bicarbonate, BeHCO3 twice, magnesium bicarbonate, MgHCO3 twice, calcium bicarbonate, CaHCO3 twice, and then strontium bicarbonate, SrHCO3 twice, and barium bicarbonate, BaHCO3 twice. Okay, so alkali metals will form bicarbonates of the type MHCO3. Alkaline earth metals will form, okay, bicarbonates of the type MHCO3 twice. See, except lithium bicarbonate, okay, lithium bicarbonate is a liquid. Lithium bicarbonate is a liquid, whereas all other bicarbonates of alkali metals and alkaline earth metals, all of them, they are solids. Okay, they are solids. Are you getting my point? Only lithium bicarbonate is a liquid, whereas the bicarbonates of all other alkali metals and the bicarbonates of all other alkaline earth metals are solids. See, when I was talking about carbonates, I have told you that carbonates are very stable. Okay, they decompose only above 1000 degrees centigrade, isn't it? Unlike carbonates, bicarbonates, okay, bicarbonates are unstable. Bicarbonates are unstable. They decompose, okay, yes, they decompose, okay, giving, okay, carbon dioxide and water. They decompose giving what and what? Carbon dioxide and water. Okay, all these bicarbonates are unstable, whereas carbonates was very stable. They decompose only above 1000 degrees centigrade, but these bicarbonates are unstable. Okay, the decompose giving rise to what? Carbon dioxide and water. For example, let us write the reaction. Let us write the reaction. Yes, see this? Okay, see if I have lithium bicarbonate, LiH, lithium bicarbonate, okay, you heat it, this decomposes giving rise to lithium oxide, water and carbon dioxide. Okay, lithium oxide, water and carbon dioxide. Okay, if I take 2 moles of lithium, you will be getting lithium oxide, water and carbon dioxide. Is that okay? Yes. Okay, now next 2 moles of carbon dioxide, or else 2 moles of carbon dioxide. Like that, if I decompose beryllium bicarbonate, beryllium bicarbonate. Beryllium bicarbonate decomposes to give beryllium carbonate, okay, water and carbon dioxide. Beryllium carbonate, water and carbon dioxide. Okay, it is quite what? Unstable. Magnesium bicarbonate. Okay, magnesium bicarbonate decomposes to give what? Magnesium carbonate, water and carbon dioxide. Okay, correct. Calcium bicarbonate decomposes to give calcium carbonate, water and carbon dioxide. Whereas strontium carbonate, okay, Sr, okay, HCO3 twice, strontium bicarbonate, okay, decomposes to give strontium carbonate, water and carbon dioxide. And lastly, barium bicarbonate, okay, decomposes to give barium carbonate, okay, water and carbon dioxide So unlike carbonates which were very stable, bicarbonates are unstable. They decompose giving rise to what? Carbon dioxide and water. Okay, now if I discuss the bicarbonates of sodium and potassium, look here, understand this point. See, sodium bicarbonate and potassium bicarbonate. Okay, yes. Okay, understand the points here. Both sodium bicarbonate, what is the formula for sodium bicarbonate? NaHCO3, isn't it? Both sodium bicarbonate and potassium bicarbonate, okay, form hydrogen bond. Are you getting my point? Yes, both sodium bicarbonate and potassium bicarbonate form what bond? Hydrogen bond. They form hydrogen bond. But okay, the hydrogen bonds, but they form, okay, different hydrogen bonds. What is this different hydrogen bond? Observe here. Okay, yes, see this. See, sodium bicarbonate will form, okay, infinite chain hydrogen bond, will form infinite chain hydrogen bond, whereas potassium bicarbonate will form dimeric hydrogen bond. What is this infinite chain hydrogen bond and what is this dimeric hydrogen bond? Are you getting my point? Both sodium bicarbonate and potassium bicarbonate will form what? Hydrogen bond, but they form different hydrogen bonds. Sodium bicarbonate will form infinite chain hydrogen bond, whereas potassium bicarbonate will form dimeric hydrogen bond. What is dimeric hydrogen bond and what is infinite chain hydrogen bond? Okay, look at this here. Yes. Okay, see, bicarbonate we have what? We have bicarbonate. What is the formula for bicarbonate? Yeah, C double bond O, okay, HCO3 minus, isn't it? Okay, OH O minus. See, this is bicarbonate. Bicarbonate. Yes or no? Okay. Yes, I can write this as C double bond O, OH O minus. Correct. This is from one sodium bicarbonate, Na plus, okay, HCO3 minus, sodium bicarbonate. Okay. Another sodium bicarbonate. Okay. Another bicarbonate. Look at here. O minus, Na plus. Okay. Na plus. Yes. So these two will form hydrogen bond here. These two will form hydrogen bond here. Am I correct? Okay. Next, I'll have one more. Yes, OH, O minus, Na plus. These two will form hydrogen bond here, isn't it? Next, okay, C double bond O, OH, O minus, okay, Na plus, NaHCO3. These two will form hydrogen bond here. So like this hydrogen bond keeps continuing. Okay, likewise, how many molecules will form hydrogen bond? Infinite molecules of sodium bicarbonate can form hydrogen bond together. That is why it is called as infinite chain hydrogen bond. Infinite chain hydrogen bond. Okay, whereas if you now consider potassium bicarbonate. Okay, what if you consider potassium bicarbonate? Look at the bicarbonates of potassium. It is what is it? Okay, yes, C, yeah, double bond O, okay, O minus K plus, potassium bicarbonate. This is one potassium bicarbonate and this is another potassium bicarbonate. Look at here, okay, yes, yeah, it is O minus, yeah, OH, K plus. This is another potassium bicarbonate. Potassium bicarbonate. These two will form hydrogen bond here and these two will form hydrogen bond here. So, okay, so here hydrogen bonding is limited only to two molecules. The hydrogen bonding is limited only between two molecules of potassium bicarbonate. That is why it is dimeric chain hydrogen bonding. Whereas here the hydrogen bonding, okay, can be formed between any number of sodium bicarbonate molecules. That is why it is called as, okay, infinite chain hydrogen bonding. Infinite chain hydrogen bonding. Any doubts with this? So I hope you have understood everything about bicarbonates now. Now, okay, see, from our lower classes, we keep studying one statement. What is it? When lime water is passed, okay, when carbon dioxide is passed through lime water turns milky. Now let us understand what is that? What is lime water? Why lime water turns milky when carbon dioxide is passed through it? Okay, don't we think we keep hearing that from our lower classes? We keep listening to it in everyday life, in our everyday life. When carbon dioxide gas is passed through lime water turns milky. We also use this as a test for carbonate, as a confirmatory test for carbonate, that is called as lime water test, isn't it? Let us learn what is that lime water test and what is lime water, why lime water turns milky. Okay, shall we? Yes. Okay, now let me write that. Let me just write that. What is it? Okay, yes, see this. We know that, okay, understand this point. When carbon dioxide gas is passed through lime water, when carbon dioxide gas is passed through lime water, okay, yes, lime water turns milky. Lime water turns milky. Correct? Milky. Okay, I'll continue my statement. Okay, if excess of carbon dioxide is passed, excess of carbon dioxide gas is passed, milkiness disappears. Milkiness disappears. Okay, disappears. This is called as lime water test. What is this called as? This is called as lime water test. lime water test, which is nothing but the confirmatory test for confirmatory in our salt analysis in our lab classes. We'll do this confirmatory test for carbonates. Okay, confirmatory test for what? Carbonates. So what is that statement? The statement says when carbon dioxide gas is passed through lime water turns milky, and if excess of carbon dioxide gas is passed, milkiness disappears. Okay, shall we think of this? Okay, what exactly happens here? What exactly happens? Why, okay, carbon dioxide, okay, turns lime water milky, and why, okay, what happens when excess of carbon dioxide is passed through lime water, and why milkiness disappears? Okay, observe here. Now, what is lime water? What is lime water? Lime water is nothing but calcium hydroxide. This is called as lime water. Now, when I pass carbon dioxide gas through lime water, see, I have told you, when oxides and hydroxides of alkali metals and alkaline earth metals reacts with carbon dioxide, they form, okay, carbonates, isn't it? Have we not discussed this in our previous video? When oxides and hydroxides of alkali metals react with carbon dioxide, they form what? Carbonates. Carbonates are highly stable and they are insoluble in water. They are insoluble in water. Are you getting my point? They are insoluble in water. Look at here, same logic is happening here. Okay, when hydroxide of calcium hydroxide, that is nothing but lime water. When lime water reacts with carbon dioxide, it forms what? Calcium carbonate. Calcium carbonate is highly stable and it is insoluble in water. Okay, therefore it forms white precipitate. That is nothing but milkiness. Am I correct? Okay, it forms white precipitate. That is why when carbon dioxide gas is passed through lime water is turning milky, because milky means white precipitate. Why white precipitate? Because calcium carbonate is less soluble in water. It is, or else it is insoluble in water. That is why it is giving a white precipitate. White precipitate means what? Milkiness. Okay. So when carbon dioxide gas is passed through lime water turns milky because of the formation of what? Calcium carbonate. Calcium carbonate is insoluble in water. It forms a white precipitate. Okay. I hope you got it. Now, when excess of carbon dioxide gas, okay, yes, when excess of carbon dioxide gas is passed through, okay, this, okay, now what is going to happen? This calcium carbonate, okay, again combines with carbon dioxide to form calcium bicarbonate. It forms calcium bicarbonate. We know calcium bicarbonates. Bicarbonates are soluble in water. Calcium bicarbonate is soluble in water. It is soluble in water. That is why the milkiness disappears. Okay, calcium bicarbonates are soluble in water. That is why milkiness will disappear. I hope you understand the logic here. What is this test called as? This test is lime water test, which is nothing but the confirmatory test for carbonate. So when carbon dioxide is passed through lime water turns milky because of the formation of calcium carbonate, okay, which is insoluble in water. Therefore it forms a white precipitate. Now if excess of carbon dioxide gas is passed, okay, so calcium carbonate will combine with carbon dioxide to form calcium bicarbonate, and that calcium bicarbonates are soluble in water. That is why milkiness will disappear. So guys, that was all about the reaction of alkali metals and alkaline earth metals, okay, formation of carbonates and bicarbonates, okay, formation of carbonates and bicarbonates, okay, yes. Now let us understand, okay, formation of nitrates and formation of sulfates. Formation of nitrate and formation of sulfate. The last two chemical properties of alkali metals and alkaline earth metals. Okay, formation of nitrates. Eighth chemical property, what is it? Formation of, okay, formation of what? Nitrates, okay, and formation of sulfates. Ninth, formation of sulfates, formation of sulfates, okay, formation of nitrate and formation of sulfates. Okay, well, look here, see, alkali metals, we have lithium, sodium, potassium, rubidium, cesium. Alkaline earth metals, beryllium, magnesium, calcium, strontium and barium. See, all alkali metals will form nitrites of the formula MnO3. Okay, all alkali metals will form nitrates of the formula MnO3. For example, lithium nitrate LiNO3, sodium nitrate NaNO3, potassium nitrate KNO3, okay, rubidium nitrite, okay, RbNO3, cesium nitrate CsNO3, correct? Yes, like that all alkaline earth metals, okay, will form nitrates of the formula MnO3 twice. They form nitrates of the type MnO3 twice. For example, beryllium nitrate BnO3 twice, magnesium nitrate MgNO3 twice, okay, calcium nitrate CaNO3 twice, okay, strontium nitrate SrNO3 twice, and barium nitrate BaNO3 twice. NO3 twice. Understood? Okay. Alkali metals will form nitrates of the type LiNO3, MnO3. Alkaline earth metals will form nitrates of the type MnO3 twice. Okay. Lithium nitrate, sodium nitrate, potassium nitrate, rubidium nitrate and cesium nitrate. Okay. Beryllium nitrate, magnesium nitrate, calcium nitrate, strontium nitrate and barium nitrate. Okay. Now see this. See, when the nitrates decompose, okay, when alkali metal nitrates, when, let me write it here, when, okay, alkali metal nitrates decompose, okay, they form, okay, nitrites. They form what? Nitrites and oxygen, okay. But there is an exception in this case, except, okay, lithium nitrate. Except what? Lithium nitrate. When lithium nitrate decomposes, it gives, okay, lithium oxide, nitrogen dioxide and, okay, yes, oxygen. Whereas all other alkali metal nitrates, when they decompose, they form nitrites and oxygen. But there is an exception, okay. Lithium nitrate upon decomposition gives lithium oxide, nitrogen dioxide and oxygen. By the way, what is the difference between a nitrate and a nitrite? What is the difference between a nitrate and a nitrite? Nitrate means NO3 minus, okay. Yes, are you getting my point? Okay. Nitrate means NO3 minus. This is nitrate. Nitrite means NO2 minus. Nitrite means what? NO2 minus. Are you getting it? Okay. Nitrate means NO3 minus Nitrite means NO2 minus, NO2 minus. So what is that I'm telling? When alkali metal nitrates decompose, they form nitrites and oxygen, except lithium nitrate, which decomposes to give lithium oxide, nitrogen dioxide and water. So let me write the reaction for it. Okay, let us write the reaction for it. Okay, what is it, students? So now lithium nitrate, which upon decomposition will give what? Lithium oxide, nitrogen dioxide and oxygen. Again, don't worry about balancing the reaction. Whereas sodium nitrite, potassium nitrite, rubidium nitrite and cesium nitrite, these will decompose, okay, giving rise to, okay, sodium nitrite. Look at the formula, NaNO2. I told you nitrite is NO2 minus, this is nitrite, are you getting it? Okay, NaNO2 plus oxygen. Potassium nitrite upon decomposition gives what? Potassium nitrite and oxygen. Okay, rubidium nitrite upon decomposition gives what? Rubidium nitrite plus oxygen. Okay, cesium nitrite upon decomposition gives cesium nitrite plus oxygen. The exception is lithium. The exception is what? Lithium. Okay, is that simple? Any doubts with this? Okay, now formation of sulfates, the last chemical property of alkali metals and alkaline earth metals. Okay, last chemical property of alkali metals and alkaline earth metals. What is it? Okay, see, we have alkali metals, isn't it? Lithium, okay, sodium, potassium, rubidium, cesium, and then we have what? Okay, beryllium, magnesium, calcium, strontium, barium, isn't it? See, all these alkali metals, all the alkali metals will form sulfates of the type, okay, M2SO4, isn't it? Like, okay, Li2SO4, okay, lithium sulfate, Na2SO4, sodium sulfate, okay, K2SO4, potassium sulfate, Rb2SO4, rubidium sulfate, CS2SO4, okay, cesium sulfate. Okay, all alkaline earth metals, all these alkaline earth metals, okay, will react, okay, will form sulfates of the type MSO4. All alkaline earth metals will form sulfates of the type MSO4. For example, beryllium sulfate, magnesium sulfate, okay, calcium sulfate, okay, strontium sulfate and barium sulfate, BaSO4. Okay, that's it. There is nothing much to deal with sulfates here. Okay, but I will take one question. What is it? Which is more soluble in water? Which is more soluble? Which is more soluble in water? We know ionic compounds are more soluble in water than covalent compounds, isn't it? Ionic compounds are more soluble in water than covalent compounds. Say I will take lithium sulfate, okay, sodium sulfate, potassium sulfate, K2SO4, okay, rubidium sulfate, Rb2SO4 and cesium sulfate, CS2SO4, okay, CS2SO4. I have got different sulfates. So which among them is more soluble? I told you, okay, we know the one which is more ionic will be more soluble in water. The one which is more ionic will be more soluble in water. And again, if I have to decide which one is more ionic and which one is covalent, I have to use what? Fajan's rule. Smaller the size of cation, larger the size of anion, more will be covalent character. More the covalent character, lesser will be the solubility in water, isn't it? Because ionic compounds are soluble in water rather than covalent compounds. See, I have again the same. I have lithium ion, sodium ion, okay, potassium ion, rubidium ion and cesium ion. Okay, as we go down the group, okay, ionic size increases. As the ionic size increases, as the cationic size increases, covalent character decreases. As the covalent character decreases, ionic character increases. More ionic. more ionic, isn't it? Okay, larger the size of cation, more will be the ionic character. More the ionic character, more is solubility. More is what? Solubility. More soluble in water, isn't it? More soluble in water. Am I correct or not? Okay, because ionic compounds are soluble in water rather than covalent compounds. Okay, understood? Any doubts? Fine. So what is the order of solubility here? Cesium sulfate will be more soluble than, rubidium sulfate is more soluble than, potassium sulfate is more soluble than, sodium sulfate which is more soluble than, lithium sulfate. Lithium sulfate is least soluble. Lithium sulfate is least soluble. Why lithium sulfate is least soluble? Because it is, okay, more covalent. It is more covalent. Understood? Since it is more covalent, it is least soluble. Any doubts? Okay. So that's all, students, with respect to the chemical properties of alkali metals and alkaline earth metals. So in the next video, we will discuss, okay, the anomalous properties of lithium, and then we'll go ahead with the different compounds of sodium and potassium. Okay, thank you so much.